Hi, Physics 2. Mr. Janowski. As promised, I'm going to be making videos about the slides we cover. Just a quick version of everything, just in case you miss class and want to get caught up with that. Or if maybe you were in class, but at the end of the chapter, you want to review the things. So here is the first part of the slides from chapters 15 and 16, Special and General Relativity. And I'm going to try to go pretty quick because I just made one of these for astronomy and it took too long. So I'm going to go kind of speedily through this. So the first thing was I asked, did everyone do the homework? If you haven't done these things, please do them as quickly as possible. The signature page of the syllabus, the student information form, and the learning style inventory. And then we sped right through this stuff. Learning styles. Yeah, they're a thing. And then I tried to do breakout groups with these people, and it didn't work because I haven't figured out the breakout groups thing yet. I'll get better at it. Don't worry. So the lesson proper started with this stuff. This do now. We learned this thing last year. So Paul the pitcher is on top of this truck. He's going to throw his 100-mile-per-hour fastball to the catcher. Alice, the baseball scout, has got a radar gun, and she's going to try to measure the speed of that pitch. She's on the truck with Paul and the catcher. Billy is standing in the middle of the road. He's got a radar gun too. He's going to try to measure the speed of the pitch. And Charlie has got a radar gun. He's going to measure the speed of the pitch. And he is standing on top of a car that's going 50 miles per hour in the other direction. So the question is, what does each scout's radar gun read? So as far as Alice is concerned, she's going to say, her radar gun is going to read 100 miles per hour because even though the truck is moving to her and to Paul and to the catcher, the truck isn't moving. The truck is at rest. The truck's not going to the right. The ground is going to the left. That's what they're going to say. Sounds a little bit weird, but it works. So her radar gun's going to read 100. Whoop, went too fast. Billy's, on the other hand, is going to read 140 because Billy's going to say, I'm on the ground and the ground's not moving, and the truck is coming towards me at 40 miles per hour, and the pitch is going 100 miles per hour relative to the truck. Therefore, the pitch is going 140 miles an hour relative to me. So his radar gun reads 140. Charlie, his radar gun is going to read, this is always the trickiest one, it's going to read 190. So Charlie's not going to say, I'm going to the left at 50 miles per hour. He's going to say, the ground is coming towards me to the right at 50 miles per hour. The truck is going another 40 miles per hour relative to the ground, and the pitch is going another 100 miles per hour relative to the truck. So they all add up to 190 miles per hour. If Charlie were going the other way, then it would be different. You would subtract one of the numbers. So yeah, thinking back to last year, Alice, Billy, and Charlie, they each have their own frame of reference, and they can all do their own physics in their own frame of reference and get an answer that works for them and they're happy with. And in a sense, they're all correct in their own frames of reference. And when you're doing it this way and you're adding these things this way, it's called a Galilean transformation after Galileo Galilei. So yeah, Galileo figured this stuff out in the 16th century, early 17th century. I forget when. But yeah, he figured this stuff out. And it's tricky if you've never seen it before, but after a while you look at it and yeah, it starts to make sense. I know how that works. So now begins story time. So this is William Thomson, the first Baron Kelvin. This is the guy after whom the Kelvin temperature scale is named after. So absolute zero is 0 Kelvin, named after this guy. Not his actual name, but his title. Yeah, peerage and royalty and all that stuff, that's all goofiness. I don't like that. It's all very backwards. But anyhow, smart guy, great scientist, did a lot of stuff in thermodynamics. And to honor him, they named the temperature scale that scientists and especially chemists use all the time. So as smart as he was, in the year 1900, he said a very silly thing. He told the British Association for the Advancement of Science, there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. So what he was actually saying is that 1900, yeah, physics is basically done. He looked around and physics, as far as he was concerned, had figured everything out. And there were little details and little things that they would measure more precisely going forward, but they were just working out the little tiny things from that point on. And the reason he said this was, for more than 200 years, since the time of Newton, the late 1600s, physics had been on a real hot streak. We had figured a lot of things out. Newton's laws of motion and all the mechanics he worked out, you can start to build things with. And then 1800s, we start to really figure out everything about electromagnetism. So now we've got the scientific revolution and the industrial revolution going on. And then Kelvin himself is mostly known for the work he did in thermodynamics, the study of energy and heat and things like that. And, in the 1800s, they figured out how to make very efficient engines and stuff like that. And it all made the modern world possible. So, yeah, compared to, the thousands of years of recorded history before that, Calvin was living at, the end of a period when science had just taken off like a rocket. We hadn't quite invented rockets that could go to space yet, but we would get there. So science was on a real hot streak. And it seemed like we were done. He was actually a little complacent here. He was being a little bit arrogant. This was hubris. This was the pride before the fall. And now, in Lord Kelvin's defense, he may not have actually said this. There's some debate about this. And if he did say it, he may have been saying it rhetorically. He may have said something like, well, there are those people who say that there is nothing new to be discovered in physics now, and the quote is just coming to us out of context. And he actually disagreed with this idea, but we don't know for sure. Point is, doesn't matter. It makes a good story. In 1900, a lot of very smart people thought physics was basically done. We had figured it all out. Good for us. So the other part of the story is in the year 1902. There's a young man walking around, knocking about in Bern, Switzerland. He had graduated from college with a degree in physics, and he tried to get a job teaching physics at a university, and he could not get a job doing that. So then he tried to get a job teaching physics at a high school, and he couldn't find a job doing that either. And so he needed work. He needed some money. So what he did is he put an ad in the paper in German, because it's in Switzerland. Some of the people in Switzerland speak German. I believe others speak French. Yes, Swiss francs. They speak German and French in Switzerland. But anyhow, this was the ad he put in the paper. And if your German's not so good, this is about what it says. Private lessons in mathematics and physics, given most thoroughly by Albert Einstein, holder of the Federal Polytechnic Teacher's Diploma. Trial lessons free. So, yeah, he was offering his services as a tutor because he needed money. And just the amazing thing is, if you were alive in Bern, Switzerland in 1902, you could have gotten Albert Einstein as your mathematics and physics tutor. And the first lesson would have been free. So, as it turns out, you don't have Albert Einstein. You have me. You have Babies. You have the other math teachers. And our rates are very reasonable. We're free. We're public school teachers. It's fine. But yeah, Einstein, the point is 1902. Yeah, he graduated college, but he wasn't a working physicist yet. He couldn't get started in physics. So that was 1902. Then 1905 comes Albert Einstein's Annus Mirabilis. The Annus Mirabilis is the miracle year. There's a few people who have had famous miracle years. Newton had one when he figured a lot of things out all in one year. But I don't think anyone's ever had as good a year at what they did in any field as Einstein had in 1905. And again, in 1905, he was not a professional physicist. I forgot to mention on the last slide, he was working as what's called a patent examiner. He worked in a patent office. Sometimes people say he was a patent clerk. That's not true. He wasn't a clerk. He wasn't filing. He wasn't doing clerical work. He was a patent examiner. So what you would do is you would come up with your invention, and if you had a good one, you would file for a patent. You would send it in to the Swiss patent office if you were in Switzerland. Einstein, with his very sharp technical mind, would look at your application, and he would decide if it deserved a patent, and he would stamp it approved or denied, and that's what he did. Because he still hadn't found work as a professional physicist. He was working in a patent office. So anyhow, this total amateur, Albert Einstein, 1905, published 4 papers in this journal, Annalen der Physik, the Annals of Physics. And the amazing thing is, any one of these 4 papers is totally worth a Nobel Prize. All of these papers were that big, that important. And he did win the Nobel Prize for one of these things, but he really could have won it for any of them or for all of them. So the first paper he published was on the photoelectric effect. And this is the one for which he actually did win his Nobel Prize. And I'm trying to be quick, so I'm not going to go into great detail. But this idea is key in the beginning of quantum mechanics. All right, so here's the detail. If you shine light, photo, on a metal, you can get electrons to pop off of this. and people had known about this for a little while, but the exact details about how it happened didn't make any kind of sense in terms of the classical physics everyone else was using. He explained it in a way that worked perfectly and is one of the keys if you start studying quantum mechanics to understanding what's actually going on. Light being a particle and a wave at the same time, basically. The next one was Brownian motion. So Brownian motion, people had known about for about 100 years at this point. Brownian motion is weird. The example we always use is if you take some very, very fine particles, like little bits of pollen in a liquid, and you look at them under a microscope, you'll see they're not sitting still and they're not all drifting smoothly. They're actually bouncing back and forth as if they were being smacked into by invisible little things. Well, they are. They're being smacked into by invisible little molecules and atoms. So Einstein's paper on Brownian motion is actually the thing that really conclusively proved that there's such a thing as atoms. Believe it or not, up to 1905, we had the periodic table of the elements for a while, and it seemed to work pretty well and explain a lot of things, but nobody was sure if there were really atoms. Well, his paper on Brownian motion kind of proved it. The third paper was on special relativity, which is what we're going to talk about in most of this chapter. And then the fourth paper was just a total afterthought to the third paper. He realized a little while after he published the special relativity paper that if those ideas are correct, it implies something else. And the thing that it implies is mass energy equivalence. So mass energy equivalence is perhaps, well, not perhaps, definitely known in a more common way as E equals mc squared. This fourth paper, total afterthought. But yeah, completely true. So now we begin chapters 15 and 16, special and general relativity. So a word on the name. What makes special relativity special? Special relativity only applies, so this is the special case, it only applies to the special case of frames of reference moving with constant velocity. So the frames of reference are not accelerating. We learned this in Physics 1, that these frames of reference have a particular name, and these frames of reference are called inertial frames of reference. So it took him 10 more years to work out the bigger theory, the theory of general relativity. General relativity explains inertial frames of reference, but it also explains non-inertial frames of reference, and it explains gravity. So general relativity is the big overarching theory. Special relativity only deals with the smaller special case. You have to say, okay, let's assume nothing is accelerating, and then you can do special relativity with that. But of course, in the real world, things do accelerate. So it took him 10 years to figure out how the general theory works. So we will start with special relativity. So there are two postulates to special relativity. The first postulate, the equivalence of physical laws. The laws of physics are the same in all inertial frames of reference. So yeah, we kind of learned that last year. If you're not accelerating, regular physics works. Newton's physics work. You can do all the physics we learned last year in an inertial frame of reference, and the rules of physics work. The second postulate is the new one. The second postulate says that the constancy of the speed of light it is the constancy of the speed of light. So the speed of light in a vacuum. Sometimes we're particular and we say the speed of light in a vacuum, and sometimes we're lazy and we just say the speed of light and we're just implying in a vacuum. But anyhow, the speed of light in a vacuum. In physics, we only ever used lowercase c to represent the speed of light in a vacuum. It is c equals 3 times 10 to the 8th meters per second. So 300 million meters per second is the speed of light in a vacuum. And the second postulate says that the speed of light in a vacuum is the same for all inertial frames of reference, regardless of the motion of the source or the receiver. So yeah, speed of light, it goes at different speeds through different mediums. The speed of light through glass or through water or even through air is not going to be this speed, but the speed of light in a vacuum is going to be 3 times 10 to the 8th meters per second, regardless of the motion of the source or the receiver. So now we do the do now again, only this time there's a change. So Paul is not throwing a baseball anymore. Paul now has a flashlight, and he's going to shoot a photon out of his flashlight at 100% c, 100% the speed of light. Alice is on the same truck as Paul. She's got a radar gun. She's going to measure the speed of the photon. Now this truck is moving pretty quickly. It's moving 40% the speed of light to the right. Billy's here on the road. He's got a radar gun. He's going to measure the speed of this photon. And Charlie is on this car going 50% the speed of light to the left, and he's going to measure the speed of the photon. So the question is, what does each scout's radar gun read? So Alice's gun reads 100% C. It reads exactly the speed of light. Maybe you're not surprised by that. The surprising thing is that Billy's radar gun also reads 100% the speed of light, and Charlie's radar gun also reads 100% the speed of light because of the second postulate. Any observer is going to measure the speed of light, has exactly the same thing. Any inertial observer will always measure the speed of light to be exactly the speed of light, regardless of their motion or regardless of the motion of the source of the light. So if we compare the old-fashioned Galilean transformation with the baseball, and if you see how these things add, and you convince yourself that this makes sense, I understand how this works, then you're pretty much destined to be very surprised by how this works. These two things, something's weird. Something's going on here. And it turns out that if we hold to the second postulate, if the speed of light must be constant for all observers, and that is true, then something else has to give. And the weird thing is, the thing that's going to give is going to be time and space. They're going to change in a rather unusual way. So whenever you learn this stuff for the first time, you always start with this idea, the light clock. So imagine that you have a light clock. This is a very, very tall clock. It is 3 times 10 to the 8th meters tall. This clock is 300 million meters tall. It's very, very big. There's a mirror at the top of the clock. There's a mirror at the bottom of the clock. And the way the clock works is every time a photon leaves one mirror and hits the next mirror, the clock is going to tick off a second. And then when it gets to the other mirror, it clicks off another second. So that's how this clock works. So imagine you're standing there in room 321, and you have your light clock. You're sitting next to it. You're watching it happily tick off, 1 second at a time. I'm going to come flying by you in a spaceship. I have a identical clock, but my spaceship is flying at some speed or some velocity v that is very close to the speed of light. So maybe I'm going 40 or 50 or 60 or 80 or whatever percent the speed of light going past you. So the question is, what does my clock look like to you? So if this is you, I really should have drawn in the stick figures. If you're standing here like this with your clock and I'm flying by to the right, you're going to see my clock going to the right. Okay, so far so good. There's nothing weird about that. The thing is, because the photon is leaving the bottom mirror at this point, and the clock is moving to the right as it goes, the photon is not going to go straight up and down. It's got to go on this diagonal line. And Pythagoras could tell you that this diagonal line has got to be a longer distance than the height of the clock. So what that means is my photon has to go a greater distance before it gets to the other mirror every time it goes off. So what that means with this weird light clock is that my clock is going to be ticking off the seconds slower than your light clock is, as far as you're concerned, because you've seen mine going to the right. It's weird, it's confusing, but that's how it is. So what that means is that moving clocks run slower. This is a well-known effect called time dilation. So dilation, if you go to the eye doctor and they put the drops in and your pupils get big, they would say your pupils are dilated. Dilated means to get bigger. So this is time dilation. The clocks are going to run slow. So common misconception. This has nothing to do with the fact that I am moving so very quickly that in a small amount of time, I'm going to be very far away from you, and it will just take some time for the light leaving me to get back to you. That's completely true, but that is not what's causing this. It's the fact that my photon has to travel a greater distance between mirrors, and it has to do it at the same speed. And the way this works is that the greater the velocity v that I'm traveling at, the slower my clock is going to appear to run to you. So it isn't just the clock that's running slower. Everything on my spaceship is going to run slower as far as you're concerned. So all the physical, biological, and chemical processes are all going to be running slower. So if I'm running some chemical experiment, you're going to say that it seems to be going too slowly. The thing is not dissolving quickly enough, or whatever happens in chemistry. I know a little chemistry. All biological processes are going to be going slower. So my beard is not going to be growing as quickly as it should be. If you're watching my tomatoes grow, they're not going to be growing as quickly. So yeah, that's kind of weird. So does this mean that I will experience life in slow motion on my spaceship? Are things going to be weird for me? The answer is actually no. Because as far as I'm concerned, me and my light clock and my spaceship, we're all at rest. We're not going to the right, which is what you say. We're going to say that we're at rest and you're going to the left. Sounds weird, but it works. So in your frame of reference, you and your clock are at rest, and me and my clock are moving to the right. And you're going to look at my clock and say that my clock runs slow. So if I were to look back at you, what would I say about you and your frame of reference and your light clock? Well, as far as I'm concerned, so I'm over here on the right next to this light clock, I'm going to say that me and my light clock and my spaceship were at rest. And you and your light clock are going very quickly to the left, which means it's your photons that have to travel the longer distance, which means I'm going to say that your clock is running slow. So both of us say that the other one has a clock that is running slow. You say that your clock is correct and my clock is running slow. I say that no, my clock is correct and your clock is running slow. So the $1,000,000 question is, who is correct? And the answer is, we are both correct in our own frames of reference. Time is completely relative. Time is not an absolute thing that ticks along and everyone can agree with. It's completely relative. And neither one of us is more right or less right than the other when we talk about our clocks. You just have to be specific and talk about your own frame of reference. So that's it. I'm curious how long this video is taking. I feel like it's taking too long. I love talking about this stuff. This stuff is amazing to me. So yeah, what is special about special relativity? Special relativity only applies to the special case of frames of reference moving with constant velocity, frames of reference that aren't accelerating. So we have a special name for these frames of reference. What are they called? These are called inertial frames of reference. And there are two postulates of special relativity. What are they? The first postulate is the equivalence of physical laws. It basically says, yeah, physics works in every inertial frame. The second postulate, the one that leads to all this strangeness and the weirdness with the time, is the constancy of the speed of light. It says that the speed of light in a vacuum, c, is the same for all inertial frames of reference, regardless of the motion of the source or the receiver. So yeah, again, the difference between how you add up velocities when you're talking about baseballs and radar guns and how you're talking about photons leaving a flashlight and radar guns and cars and trucks moving at some large fraction of the speed of light. Yeah, the weirdness comes in because of the second postulate, the constancy of the speed of light. That's it for this time. Hopefully you guys found that helpful.